Our next speaker is Lisa Peltason from Hoffmann-La Roche.
I'm Lisa Peltason. I'm working in the cheminformatics and statistics group at Roche in Basel. And I'm presenting to you today the SAR Analyzer, which is a software platform that is actually currently being developed at Roche. And its purpose is to provide an intuitive visual analysis of structure-activity relationship data. In medicinal chemistry, as virtually in every field else, we're facing a situation where the data which is available, the amount of the data is rapidly growing, and decisions have to be made fast and efficiently on the basis of multivariate data. So we felt that we need a tool that really helps people to navigate complex data landscapes. So this is the idea behind the SAR Analyzer, and its major purpose is to really provide an intuitive access to SAR data to medicinal chemists, and of course also to support the decision-making process. So to make this clear, we're not talking about any kind of quantitative predictions today. It's just to show to people what is in the data and help them to quickly browse through them. So our approach to that is to offer a portfolio of different tools that should be interactive and all focus on information-rich visualizations. So this is really our major focus: offer visualizations that can also be intuitively navigated through user interaction. So our approach to that is mainly not developing novel methodologies from scratch, but we're just evaluating the methods that are out there on the market, and we're combining and adapting different methods to best fit our own workflows and requirements. So maybe some words about the implementation. So the entire platform is being developed as a Java application. We're building on the Eclipse-rich client platform, which enables us to have some kind of a plug-in architecture where different visualization tools can be plugged into the core data analysis tool. So we really achieve very flexible and customizable workflows. At this point, at the moment, actually we're in the middle of evaluating different techniques, developing prototypes, and these prototypes are actually standalone Java applications, so they can be brought directly to the desks of medicinal chemists. At the moment, we have some volunteer test users. At the core of these, all these tools, we have the ChemAxon functionality. We're using the Java API of JChem, Marvin, and screen packages for data import, internal and external representation, and different algorithms. So today I'd like to specifically focus on the SAR Tree prototype. It's built on a recently published visualization technique that was developed in the group of Jürgen Bajorath at the University of Bonn in Germany. And it actually tries to address the very basic SAR questions in a visual way. So these questions might include, of course, how do chemical structures alter, or chemical modifications alter the biological activity of active molecules? Are there any trends in the SAR, and can we make them visible in the tool? How is biological activity actually related to other molecular properties that are relevant in any project? And finally, can we detect activity cliffs, which might be very similar compounds having a substantially different biological activity? So these are the basic questions that we're trying to address. The SAR tree is actually such kind of a data structure here. We have a tree which is similarity based, and each of the nodes in the tree actually just represents one molecule. Each of those nodes is colored according to biological activity or any other user-selected property of the molecule. And edges connect molecules that have the most similar chemical structures. So here we have nearest neighbor relationships along the edges. And another rule within this tree is that the similarity of the compounds from top to bottom decreases. So we have, in the first level, we have molecules that are nearest neighbors to the root molecule. And as we move down in the tree, molecules become increasingly dissimilar or structurally diverse with respect to the starting molecule, which would be at the root. So this constraint helps us to intuitively navigate such a tree. When we navigate such a tree, we look at those pathways here, starting at the root and ending at a specifically selected molecule. And those pathways really now convey SAR information because they denote sequences of molecules that have gradually changing structures. And if we combine that by looking at potency or any other properties, we can directly visualize what happens when we modify a certain structure. I will show some examples later on, so that should become clear. But first, I'd like to show you a bit more detailed how this tree is actually constructed. We start out with any set of molecules somewhere in chemical space. At the moment, we just load an SD file. And the first step is to select the reference molecule, so the molecule that sits at the top in the tree. This reference molecule serves then as a basis, and we define a similarity radius around that. So all the molecules that fall in this similarity radius will then become part of the tree analysis. So of course, for doing this kind of calculations and for the entire tree construction, we need to calculate pairwise similarity coefficients, and this is one thing where we heavily rely on ChemAxon functionality. We have as a default, we represent the molecules via the hashed chemical fingerprint, which provides a topological similarity measure. However, it is also possible to just select any other kind of fingerprint. For example, the pharmacophore fingerprints provide a fuzzier similarity relationship. And it is also possible to load in some custom feature list fingerprints from the input that might have been calculated with some external program. So having these fingerprints, of course, we need similarity coefficients to compare them, of course. Here the default is to use Tanimoto, but Tversky or the normalized Euclidean dissimilarity is also possible. And then we just take the complement of these values to obtain the similarity. Okay, so this is how we start. We have now the set of molecules that should become visible in the tree, and we have the similarity relationships. And now we go on and put the reference molecule at the root of the tree, and we add subsequently all other molecules to the tree. And there are basically three construction rules to that. So when we have a molecule B that should be added to the tree, we of course have to decide where to add it in the tree. The first rule is we will add it to its nearest neighbor. So when we want to add B to the, we want to add B to the molecule A, we must ensure that A is the nearest neighbor of B. And also we introduce nearest neighbor threshold in order to make sure that we connect only molecules that really have a significant level of molecular similarity. And finally, in order to ensure that the similarity actually decreases from top to bottom in the tree, we have the rule that we may only add B to A as a child if B is less similar to the root than A is to the root. So this will ensure that we really have the molecules in the tree sorted or ordered according to their similarity to the root level. So this is basically how the tree is constructed. And having this as a prerequisite, we can now just look at the prototype that is shown here in its current form. So we have this kind of a setup where on the left we have a molecular data spreadsheet. Just some technical issue, we are not using Marvin spreadsheets here because Marvin is swing-based. Our system works with SWT, and we try to keep these two worlds as separate as possible. So those are currently only images, no live structures in the spreadsheet. The most important part of the tool would of course be the center part where we have the tree and path display. Here we use the Eclipse Zest toolkit to have an interactive visualization of any kind of networks, basically. And on the right, we also have a control panel where the user can just set different display and calculation parameters. So now I'd like to show you a very small application example just to see how one could use this tree. Here I've just selected a publicly available data set of adenosine receptors, receptor inhibitors in that case, or antagonists. It's a Campbell data set which was part of a publication also published by the Bio-Rad group again. In this tree here I have colored all the molecules according to the logarithmic affinity value towards the A2A receptor subtype. And the coloring ranges from red for baseline activity of lower than or equal to 10 micromolar, and it ranges via yellow to over to green, which indicates a peak activity of 1 nanomolar or higher. So these levels and also the colors are completely under user control, so the user can define the coloring and the resolution and all the levels, and then the tree structure or the colors would be updated on the fly. So in order to navigate such a tree, we would look at individual pathways, which I already mentioned. So here we see such a part here where we look at the sequence of molecules starting at the root molecule and leading down to that leaf molecule here. And already we can see from the coloring that in the beginning not much happens when it comes to potency. So here the line indicates the A2A pKi, and here is highlighted every modification as compared to the previous molecule. And we can see here that actually modifications have mostly taken place at this point, and in those first 5 molecules, activity basically stays the same. However, when we move on, we can see here at least a slight increase in potency, which of course is now really interesting to relate to the modifications that have been made. And for the scientists, this is really the way how to directly relate the modifications that have been made to their potency or to the effects that these modifications had. This is not, of course, not the only series or not the only sequence of molecules you can look at. When we look at this tree section here, we see that there's another branch that obviously leads to a molecule which is much better in its activity, as indicated by the green color. So we can also just switch to that path. In the tool, you would just double click on the node and you would be displayed this pathway. And here again, we can see the first 4 molecules are the same as before. Now we have this molecule where actually 2 modifications have been introduced that have really a good impact on the potency. So we have here a really good potency increase. Actually, we can see that potency is increased by more than 2.5 orders of magnitude. So this would be really an example of such an activity cliff, which I mentioned earlier, where we have very similar structures, but a sudden leap in potency. So this is, of course, a point where people can really learn a lot about the SAR, and in this colored tree representation, the attention is directly drawn to such interesting points in the SAR data set. So, of course, that is only one thing that you can do. You can browse and navigate your data with this tool. Another very important aspect, of course, is to look at multiple properties. So for this, I've just shown the same path as just before and added a line plot for the pKi value for the A3 receptor subtype. And we can see that obviously in this sequence of molecules, we have a steady increase in potency for the A3 receptor subtype, whereas right at the end we have very similarly high potency for both receptor subtypes in this molecule, which would indicate that this one might not be such a good choice if we were searching for a selective molecule. So this would really direct the attention to that, and also maybe make it clear that one should look for backup structures as well. Okay, so to elaborate a little further on this, also, of course, one can also compare the entire trees colored according to different properties. So here we have at the top the tree colored according to the A2A subtype, and at the bottom the exact same molecular structures displayed in the tree, but only colored according to the A3 receptor affinity. And so something that really strikes the eye here is that apparently this part in the tree contains always structures that are very active for the adenosine receptor A3 subtype, whereas they have only weak or moderately high activity for the A2A subtype. So this means that actually here we have a whole bunch of A3 selective compounds. And of course, we would like to know, what about these structures? Is there anything that we can learn from that? Do they have something in common? And actually, we're not quite there yet. So as I mentioned, we're in active development. But this is really a very important point that we're directing our future work on, to just mine the data for patterns so that we can annotate different regions in the tree with just some structural features or even property ranges that specific compounds have in common. So this would even make the SAR behavior in such a data set more visible. So this is one part that we're focusing on now and in the future. Another thing I already mentioned, that we want to support really the decision-making process. So we're also setting up functionality for user annotations, storing and sharing session information, so that really decisions and analysis can be stored, shared, and tracked. So this might be, for one thing, very interesting for project managers who want to have a look at how successful or what has been done in this project, but of course also for new members joining a project to just quickly get an overview of what has been done in the project and where he or she could jump in. Yeah, so I'd like to conclude with just some key principles. They really sound almost trivial, but I think you cannot state them often enough. So really one thing is we have to keep things simple, at least on the surface. So there's no use overloading the visualization and the interface because afterwards people won't like to use the tool. So on the surface, we're deliberately aiming at keeping things simple. Of course, the science behind shouldn't be oversimplified, but I think the strengths of this approach is to have really a flexible and intuitive user interface, so people can really interact with the data in real time. And of course, something that we always should keep in mind, that projects like these are there to support, but not try to dictate the expert's workflow. So this is really some bullet points that I'm also keeping in mind while developing this project. Okay, so this is just the colleagues that really contributed to the project. Members of the cheminformatics group and the research informatics for their informatics support, chemists who have volunteered as guinea pigs and really did a great job giving critical feedback, and of course the business owner and project sponsor. Okay, so that was it already. Thank you for your attention, and I hope there's at least some time for questions.
It's not a question, it's just a suggestion. In your tree, instead of taking a root molecule, take a root scaffold representing a series, and then underneath you put the R groups, and then you decompose the R groups, and you will see many more things and many more patterns.
That's really a very good point, and actually, yeah, we're planning on doing that. Yeah, just having the user sketch a scaffold and get all the molecules belonging to that scaffold. However, interestingly, I also got some feedback from chemists who told me, oh, R group decomposition, actually that wouldn't show me so much new. So those chemists really mentioned that they appreciate having the fuzzy fingerprint similarity search because that would highlight similarity relationships that are not really obvious. So there's actually those two parts, and we should probably go along both paths. That's true. Thank you.
I'm wondering if it would be useful to use maximum common substructure searching for similarity, because you were showing the modifications, and I guess you were using actually maximum common substructure searching for the visualization of the differences. I'm not sure.
Yeah, that's true. So at the moment we're not having the common substructures visualized, but that would be also something that would facilitate the navigation in the tree, that you have, that you maybe can select molecules that have a certain substructure, or annotate subtrees with the maximum common substructure of all the molecules in the tree. That's a really good suggestion. Yeah.